Okay, for this review problem, we're going to prove this theorem that has an if and only if in it. We will prove that n is odd if and only if there is an integer at j such that n is equal to 2j minus 1. Ordinarily, we say n is odd if we have 2k plus 1. This time it's minus 1 instead. Okay, now this is an if and only if, which means I have to prove two different things. Okay, so first off, suppose that n is odd. So I'll suppose this. I'll need to end by showing that there's an integer j such that n is equal to 2j minus 1. Now, if n is odd, by definition, there is an integer k so that n is equal to 2k plus 1. All right, now that's well and good, but I want a minus 1 there. Therefore, n is equal to 2k plus 1. Well, I want to have something with a minus 1. And so to compensate, I'll change the plus 1 there to plus 2 minus 1. Now that seems like an unusual step. Ordinarily, you would take this more complicated thing and turn it to the simpler thing. But I'm going to force this to have a minus 1 in it to match the minus 1 that I want to have there. So the minus 1 stays by itself, and on these two terms, I can factor the 2 out. Okay, now we basically have it now. Let j be equal to k plus 1. By the axioms of arithmetic, j is an integer. K is an integer, 1 is an integer, and therefore j is also k plus 1 is also an integer. And we have the desired conclusion that n is equal to 2j minus 1. Okay, so that's one direction. Now the other direction. And let's see if I can get it on the screen. The other direction. Now I suppose the second statement, and then I will prove the first statement. So suppose that n is an integer with n is equal to 2j minus 1 for some integer j. Okay, so suppose that n has the required form, 2j minus 1, where n is an integer. I want to show that this n is also odd. Then, kind of like what we did before, n is equal to 2j minus 1. I don't want a minus 1, I want a plus 1. And so to force that, I'll have a minus 2 there to compensate. So minus 2 plus 1, and then 2j there comes along for the ride. And so the first two terms, I can factor the 2 out, and I'll leave out the plus 1. So this has the required form. Let k be equal to j minus 1 by the axioms of arithmetic. K is an integer because j is assumed to be an integer and also 1 is an integer. So by definition, n is odd. And that's the end of the proof. Okay, so this was an if and only if, and so I had two different proofs to do to prove this theorem.